So in this video, we're going to talk about convergence of Taylor series. And I do want to remind you just of like how these videos work because I'm going to throw a lot of information at you in this video. I do intend for you to pause, think, and try examples. So I'll remind you of that from time to time, but I'm going to be throwing a lot at you and I'm not expecting you to just magically get it. Like some of it is, it helps when you stop and think a little bit. Okay, so we're talking about convergence of Taylor series. So before we just talked about like what is a Taylor series? Like how do you make it? So we were practicing generating these Taylor series by f at x equals a. So we were practicing writing out like this whole like formula, right? And okay, so a Taylor series is a very strange thing to wrap your head around. What it says is that a function f can be rewritten in series form. And this just feels so weird. Like, what? So today we're going to talk about like how can I actually believe that a function can be rewritten in this series form? And so I've got a couple of theorems to help us with that. Okay, so first let me just state Taylor's theorem. So if f and its first n derivatives are continuous on the closed interval between a and b, and the nth derivative is differentiable on the open interval between a and b, then there exists a c in that interval such that f of b equals f of a plus f prime of a times b minus a, so on and so forth, up to the nth derivative of a over n factorial times b minus a to the n. Okay, so this first part looks like, what you were practicing before with the Taylor series. The thing I want to highlight about this is that this Taylor's theorem has this end point. It is the n plus 1 derivative at c over n plus 1 factorial times b minus a to the n plus 1. So we've got this n plus 1th term, and we've plugged in some value c. So this is kind of an interesting thing. What is this last thing? This is an error term, and that's what we're going to be exploring today. Something that makes Taylor's theorem a little weird is that usually, so we have all these b's in here, usually this is an independent x. So Taylor's theorem kind of opens the door for us to use Taylor's formula. So I'm going to show you that next. So if f has derivatives of all orders on an open interval I containing a, then for each positive integer n and for each x in I. So this is almost the same thing, except now we've just rewritten everything in terms of x. So this is actually the thing that's kind of important today. So f of x is going to equal, so the first n terms of the Taylor formula plus this r sub n of x, where this r sub n of x is once again this n plus 1th term with c plugged in here. Okay, so this is kind of where we're going to spend our time today. Understanding this error term, how to maybe estimate it, and what it means. This is actually pretty important. So this is, like I said, it's the error. And really, I think what like Taylor's formula is telling us in essence is that we can rewrite our functions in terms of this nth degree Taylor polynomial and then this r sub n of x. So we've got this polynomial approximation plus the error. So Taylor's formula is telling us that we can write a function in this way. Okay, so here's the part that's kind of important. If r sub n of x goes to 0 as n goes to infinity for all x in the interval, we say that the Taylor series generated by x equals a converges to f, and f of x equals its Taylor series. Okay, this is some important stuff here. This is really key. So this is kind of why this error term matters and why we care about it so much. If it goes to 0, then that means that our Taylor series converges to f. So this is giving us a guarantee now that our function rewritten in this series form, that these are actually equivalent. It's kind of a crazy thing that you can rewrite functions in a series form, but that is what this is guaranteeing to us. And also, I want to just state here, we can usually estimate the error without actually having to know the value of c. So I'm going to show you all of this in the next example. Okay, so we're going to show that the Taylor series generated by f of x equals e to the x at x equals 0 converges to f of x for all values of x. So we're going to explore a little bit with the error and how to play around with it and all this stuff. So let's first start with our Taylor series. Okay, so the nice thing about e to the x is that the nth derivative is just always e to the x. So then if I plug in 0 for any of those derivatives, it just always equals 1. So I strongly encourage you to just write out what does the Taylor series look like. So just write it out to the nth term and then hit play. Okay, so I told you to write this out to the nth term, just as a little bit of a review exercise here. So I want you to notice the slight tweak. So today we're using Taylor's formula, and I've written this out to the nth term plus r sub n of x. Okay, and remember, what does the r sub n of x equal? Well, I would like for you to once again pause the video and just reread the part about what r sub n of x equals and write out what it should equal in this case, and then hit play when you're ready. So my r sub n of x, if I plug in my c, it's going to be this e to the c over n plus 1 factorial times times x to the n plus 1. Okay, so I want to take a moment just to pause and think about what we can say about this error term, this r sub n of x. So we know that r sub n of x is this e to the c over n plus 1 factorial times x to the n plus 1. So it's for some c between 0 and x. And I really want to explore like what this actually means. So remember, this series is centered at a equals 0. But the thing that's weird about this with this x, so the order of this, x can be anything, okay? So we could actually have x be positive, so our c would be between 0 and x, or my x could be negative, which would mean that my c is between x and 0. So we don't know, so we're going to consider all of those possibilities. So to that end, if c is between 0 and x, then e to the c is going to lie between e to the 0 and e to the x. So we're going to consider some different possibilities of c. And there's two things that I want to kind of investigate here. So the first is just, can we estimate what this r sub n of x is? How could we do that? And then second, this really important thing that I told you about, that as n goes to infinity, like what does this equal? So we're going to break these up into two pieces. So first, I just want to think about like, what is the deal with this c? Like, how can I estimate what the error is? Okay, to figure out what c is, we have to actually think about the different possibilities of x. And like I said, x could be negative. So if x is a negative number and c falls between x and 0, then c is going to also be a negative number, right? Because it's between x and 0 and x is negative. So then e to the c is going to be some fraction, so this will be less than 1. Okay, what if x equals 0? If x equals 0, then our error term is actually just going to equal 0. And then finally, what if x is positive? So if x is positive, then c is also going to be something positive. So x is going to be the highest number in this interval, and so then e to the c will be something less than e to the x. Okay, so depending on what the value of x is, that's going to help us figure out what the value of the error is. So I can plug in any x that I want. And it's not like I don't have to know exactly what the value of c is to figure out what this error actually is. So let's pretend for a second that x is some number less than 0. So what can I say about the value of the error? Well, remember, if x is something less than 0, then we said that this e to the c is going to be some value less than 1. So this error term will be something strictly less than this. Since this is something less than 1, this will be less than whatever our value of x actually is. So this will be something smaller. So I don't have to know necessarily what the error term is, but I know like what it's bounded by. And this kind of gives me some hint as to, you know, what it could be close to. And then when x is something greater than 0, so then using that equality that we had before, so this e to the c is less than this e to the x, so this whole error term will be less than e to the x times x to the n plus 1 over n plus 1 factorial. So this gives us a really open way to think about just what the value of error terms like are, depending on what value of x we choose. So this is a way to just explore what that is. Okay, so now that we've talked about that, let's talk about the other part of this where we want to figure out what's the limit as n approaches infinity. And so in this case, sorry, I've just rewritten this slightly. So let's take, what is the limit of this, of e to the c times x to the n plus 1 over n plus 1 factorial? Okay, so the e to the c, this is some number. I don't actually care what it is. This is actually just a constant. So all I really care about is what's going on here. And this is actually the form of a common limit that we've talked about before. So that x to the n over n factorial, this just equals 0. So I can just take this for granted. So this whole thing then equals 0. So the e to the c value, this value doesn't even matter. This is really what matters. So what's important here is since this goes to 0, that guarantees that our error went to 0. So that guarantees that our series converges to e to the x for every x. So this is a really powerful idea now with the error term. I determine what the error term is, kind of what the format of it is. If I know that it goes to 0, then I can trust that my series converges to the original function. And so what that means then is e to the x equals this series, can be rewritten as this series, or like this. So these theorems have built up the trust to believe that this series does indeed converge to e to the x for any value of x. So one thing that means then is that like e to the 1 is actually just 1 over k factorial. We can approximate e as a series. Kind of crazy, right? Okay, so I want to just take a moment now to remind you of what does it mean, though, for a series to converge. So let's just take a short field trip just to kind of explore. Okay, so here we are at Desmos, my favorite website for exploring and playing around with these things. Okay, so this black line here is e to the x. So that's the actual function. So these Taylor series are supposed to approximate e to the x. Okay, so the idea then of convergence for all x is that if I could take this series out an infinite amount, what should happen is that the series itself should eventually line up with every single value on this curve. So if I continue to back this out for forever, with an infinite amount of terms, my series would line up perfectly with the graph of e to the x. So let's explore that a little bit. So here I just have out to x to the third. So I've just got the first 4 terms of my Taylor series. So let's just look at how well this kind of lines up. Okay, so this is not the best estimate, right? But it does definitely overlap for part of the graph. Okay, and that kind of makes sense, right? You wouldn't anticipate that if I just had a couple terms in the series that this would be the best approximation for the graph. So, okay, let's back out there. So now, let's see, how many terms did I take this out to? I took this next one out to 8 terms. So let's see how well this approximates. Okay, so now this is doing a much better job, right? It actually lines up pretty darn well at 8 terms, but it doesn't line all the way up with the graph. So it's got a point where it kind of drops off. So that error term would actually help us figure out kind of where our drop-off terms could also happen. Okay, and then let's take this out one more time. So now I've written out, let's see, how many terms did I write here? I wrote out 15 terms of this series for this last one. So if I take out 15 terms, so now it's lining up again a little bit farther. So what does convergence mean for all x? It means that if I were to take this out to enough terms, an infinite amount of terms, this pattern that we see of getting closer and closer of lining up to the graph, we are guaranteed that in an infinite amount of terms, this is actually going to line up perfectly. That is what the Taylor series actually is getting at, and that's what the infinite series is guaranteeing. So if I can expand this out to enough, values here, this series will line up with e to the x for any value of x that I want. That is what the Taylor series means. Okay, so let's keep going with this. So the next thing I want to talk about is the remainder estimation theorem. So if there is a positive constant m such that the n plus 1 derivative at t is less than or equal to m for all t between x and a inclusive, then the remainder term r sub n in Taylor's series satisfies the inequality r sub n of x is less than or equal to m times x minus a to the n plus 1 over n plus 1 factorial. Okay, so let's break down what this means next. If this inequality holds for every n, and the other conditions of Taylor's theorem are satisfied by f, then the series converges to f of x. So again, this is another way of talking about this convergence. So these error terms are actually pretty important. So we need to be able to show that this inequality holds. So let's do that now in the next example. So let's show that the Taylor series for sine of x at x equals 0 converges for every value of x. Okay, so what I want to do is first I want to set up the Taylor series. So I would actually like to ask you to do this. I think this is a really great practice. So, first start setting up your derivatives, and then you can start evaluating them at x equals 0. So you can pause here and hit play when you're ready. Okay, so here are just my first 4 derivatives. I just always like to see kind of how this cycles, and I can see that if I start plugging in 0 for all these derivatives, so I get this 0, 1, 0, negative 1, 0. So there's this pattern that emerges for sine of x. So at the odd derivatives, I have a value of either 1 or negative 1. So I can write this as for the 2 plus kth derivative at 0, this will be negative 1 to the k. So if I want to have the first derivative, so if the first derivative equals 2k plus 1, then that would mean that k has to equal 0, and so negative 1 to the 0 will just equal 1. So that's the way that works. You could have written this in a slightly different way and still have it be equivalent. So if you didn't write it exactly like this, but you still had, kind of this equivalent form, that also works. Okay, so now what I want to do is I want to set up my whole Taylor series, or my set up this format. Just remember that we are trying to use Taylor's theorem here. So, and I went ahead and I plugged in all of these different values. So the way that I want to set this up is I now want to be able to categorize this pattern. So if I set up the pattern up to the first, we'll do to the first k terms. So here's my first k terms in the series. And then, so the next thing that I want to do to prove my convergence is I need to set up now this error term. This is the thing that's going to prove the convergence for every x. So when I'm asked to prove convergence, I have to now get used to setting up to the first kth or first nth terms, and then I'm going to do the next k plus 1 terms. Okay, so let's think about, for a moment here, just the values of sine of x or any derivatives. So for sine of x and all its derivatives, the values are always, the absolute value of that will always be less than or equal to 1. So because of that, so if I go back to the remainder estimation theorem here, so remember, we're looking for some positive constant that bounds my derivatives. So in this case, that constant would be equal to 1. So my m is going to equal 1 from the remainder estimation theorem. So now, using this format, I can plug in my 1, and I can plug in all the things that I've got. Actually, this might be a great place for you to pause and maybe fill this in, and then hit play and kind of analyze it. Okay, so if I plug in everything for this particular problem, so remember my index in this case, I'm not just using a k plus 1 index, so I'm using a 2k plus 1 index. So the next term in this case then would be 2k plus 2. So that's the next term. So this will be x to the 2k plus 2 over 2k plus 2 factorial. And so now that I've set this up, I just need to think about what happens as k goes to infinity. So if I take this limit, okay, well, once again, this is that same common limit, right? This limit that we just talked about. So I know that this is going to equal 0. So once again, this is why these error terms are so important. Once I get that this converges, then that means that the series converges to sine of x for all x. So that theorem guarantees now that sine of x can be rewritten as a series. And if you wanted to play around with this and start, writing out more and more terms in the series, you would find that this series lines up very well with the graph of sine of x. So let's talk about now using our series in a couple other examples, and just like what are other ways that we can kind of play around with this. So I want to use known series to find the first few terms of the following Taylor series. So we're moving away from the errors now, and now we're just kind of playing around a little bit more with other Taylor series. So let's say I've got 1/2 times 3x plus x cosine x. Okay, so how would I write out this Taylor series without creating a huge nightmare for myself? Well, what I can do is first I can distribute, just using, distribution laws. So where does the Taylor series fit into this? The Taylor series is going to fit in for this cosine of x. So this is where I'm going to rewrite with the Taylor series. So I'm going to replace cosine of x with the Taylor series, as you see here. And then I can distribute this x over 2. And then I will get for myself, here's my new Taylor series expansion for this function here. So I don't have to reinvent the wheel if it's a known Taylor series. Okay, so let's try that one more time. Let's try this for x squared sine of x. So you don't have to do this for x squared. It's just sine of x where you have to do that Taylor series expansion. So write out just the first few terms of the Taylor series for this using your known Taylor series. Pause here, hit play when you're ready. So if I replace sine of x now with my Taylor series, I get this. So here's my Taylor series expansion of this function. So not all functions you have to do all this like crazy work. And this actually is good to know, right? That I can just replace a known Taylor series here, because otherwise this would be a real nightmare to have to probably sit down and figure out. So if you can use a known Taylor series, that's just something good to know. And I want to do one other example in this video. So for what values of x can we replace sine of x by x minus x to the third over 3 factorial and obtain an error whose magnitude is no greater than 3 minus 10 to the negative fourth? Okay, so now this is talking about what values of x, will ensure that we get a particular magnitude of an error. Okay, so first of all, let's just look at the Taylor series expansion of sine of x, which is as shown. So up to this point, up to this pink line, this x minus x to the third over 3 factorial, this is where I want to kind of cut off this question, right? Because it says, can we replace sine of x by x minus x to the third over 3 factorial? So I want to replace sine of x by this and obtain an error whose magnitude is no greater than this. So to ensure now that I get the error that I want, if this is where I want to cut off the series, then using what we've talked about with error terms, I need to look at the next term, this x to the 5th over 5 factorial. So what I want to do now is I want to take that term and I want to figure out for what values of x will ensure that I stay under this 3 times 10 to the negative fourth. Okay, well, at this point, this is just an equation that I have to solve, so I can multiply 120 over to the other side. So 3 times 120 is 360. So now I need x to the 5th less than 360 times 10 to the negative fourth. And then I can just finish solving this. So I need that the absolute value of x has to be less than the 5th root of 360 times 10 to the negative fourth. So when the absolute value of x is less than 0.514, that will ensure that I can replace sine of x by this and get the error whose magnitude is no more than the error that I wanted. Okay, so lots of stuff, lots of different examples, but I'm gonna leave it there and I will talk to you guys in the next video.